Let's do another liquid-liquid extraction problem. In this problem, we have a column with a set number of stages, free equilibrium stages, and we're tasked with finding the concentration and flow rates of the exiting and entering streams based off of the composition data that we already have. So let's start by just writing down what we know. So we have first the feed stream F, and this has a flow rate of 1,000 kilograms per hour, and a composition of acetic acid, water, and IPE. And this composition is going to be roughly, in terms of weight fraction, 40% acetic acid, 60% water, and 0% IPE. And then we're also going to add a column for the component flow rate. This is also going to be in kilograms per hour. And this is simply going to be the flow rate multiplied by the weight fraction. So this is going to be 1,000 kilograms per hour times the corresponding weight fraction. And now we can do this for every other stream. So we're primarily interested in the entering and exiting stream, since those are the concentrations and flow rates we need to find. So let's just copy paste this table for every other stream. Now the next step is to simply draw our equilibrium diagram. So we have the equilibrium data here. We're just going to go ahead and choose water as the x-axis and acetic acid as the y-axis, and this is always completely arbitrary, but it's up to you to decide which way you want to plot it. But the important thing is to make the axes consistent. So if you're always plotting water in the x-axis, then you need to make sure that you always plot water in the x-axis. So let's do the water layer first. So water in the x-axis and acetic acid in the y-axis. And the water layer is going to be simply this value. And there we go. And then the next one is the IPE layer. And once again, we're going to choose water as the x-axis and acetic acid as the y-axis. And there we go. So now we're just going to make a few changes to make the graph a little nicer. Okay, so now we've drawn the graph, and now we can get started on solving this problem. Well, now first of all, there's an issue here. We don't know the flow rate of the entering solvent, so that means that we can't conduct an overall mass balance. So the general approach of calculating the mixing point is not going to work, because we don't have the composition nor the flow rates. Therefore, we need to think about another way of approaching this problem. So we first should take a look at the exiting extract stream. So we know that this stream has a composition of 20% acetic acid, and we also know that since it is exiting the last stage, it needs to be in equilibrium with this stream here, Rn. What this means is that it is essentially going to be, the composition is essentially going to be on the phase boundary, on the extract side. The extract side is this orange side here. So if we look at acetic acid, we can see that the extract stream is going to have a composition around here. Now if we look closely, it looks like this is about 6% water. So let's go ahead and write that. And this means that obviously IP is just going to be equal to 1 minus the other compositions. So now we have the composition of the exiting extract stream. Given that we don't know the overall flow rates, is there still a way that we can perform stage-by-stage balances? As a matter of fact, there is. So we know that there is effectively in countercurrent systems, there is a delta point, and when we do the stage-by-stage balances, all of your construction lines need to pass through this delta point. Now normally we calculate the delta point from forming overall balance, but we can also just calculate the location of the point ourselves by taking the difference between two streams at the same point in the column. So the delta point flow rate is simply the difference between the extract and raffinate streams, and then the composition, or I guess the position of this point on the graph, is going to be the difference in the component flow rates. So let's go ahead and do that. So let's define a delta point, and this delta point value is going to be equal to En minus the feed flow rate. So that's going to be 1500, and then we're going to have a difference in flow rate for each of the components. And now we can convert this to an x or y coordinate value by simply dividing by 1500. Now, because our graph is using acetic acid and water, that's what we're going to use to plot on the graph. So let's select data and add a point. And the x value is going to be water, since we use water as our x-axis, and then the y-axis is going to be acetic acid. So there you go. So there's our delta point. What this means is that when we do the stage step down, every single one of those lines needs to pass through the delta point. So before we proceed, let's just go ahead and trace the tie lines. Okay, we have our tie lines, so let's just go ahead and trace our first equilibrium line, which is the equilibrium line between En and Rn. So we know where En is; it's about here. So we trace this line, we're going to end up approximately around here. So that is going to be Rn. Now we want to step down to En minus 1, and to do that, we're just going to trace a line from Rn and trace it all the way to the delta point. There. And where this line intersects, and let's just change this color so that we can differentiate it. And where this line intersects with the extract line, this is the composition of En minus 1. So let's keep doing that. Okay, so now we have 3 equilibrium lines, and this is equivalent to 3 stages, so we know that we have to stop here. So just as a final sanity check, let's just check the composition of our feed line and make sure that it is collinear with the En point and the delta point. And it is indeed collinear, so that means that our delta point was correctly positioned. And so now all we have to do is take a look at the final compositions, and then we can calculate the flow rates. So the final raffinate flow rate looks like it's about 67% water and about, I'd say, 29.5% acetic acid. So let's go ahead and write that. So 0.295 and then 0.267, and this leaves So now we know the composition of the raffinate stream. How do we use that to find the flow rates? Well, we know that the entering solvent stream contains no water, so that means that the balance of water needs to be contained within these 3 streams. So we have the extract stream, and the raffinate stream that add up to equal the water entering from the feed stream. Therefore, this flow rate is equal to 600 minus 150, which is 450. Since we know the composition of this stream, we can find the total flow rate by simply dividing by the weight fraction, which gives us 671 kilograms per hour. Knowing that, we can now conduct an overall mass balance and find the flow rate of the solvent stream. So the solvent stream is equal to 2500 plus 671 minus 1000, which gives us 2171 kilograms per hour. Now that we know that, we can easily find the remaining weight fractions by simply performing some mass balances. We know that this acetic acid flow rate is once again equal to R1 plus En minus F. And we can say the same thing for the IP flow rate. And then the weight fraction is simply by definition the component flow rate divided by the total flow rate. And with that, that gives us all the values that we were looking for. The exit raffinate concentration, which is simply R1. The required entering extract stream concentration, which is E0 or S. And then the flow rates,